Hello, everyone. It's nice to see that many of you connected on this Sunday afternoon. So to remind you, we are here in this AI research school phase. It's the second phase of the school. So first phase was the intro to Python. Now we move into the more technical knowledge on machine learning and deep learning. The last workshops you've had so far were an intro to AI and classical machine learning. And today we're going to focus more on deep learning, thanks to our instructor, Dr. Parsa Bagazadeh, that I'm really happy to introduce today. So Parsa obtained his PhD in computer science from Concordia University under the supervision of Professor Sabine Bergler, and he was a proud member of the CLAC Lab, which stands for Computational Linguistics at Concordia. In his PhD, he focused on the integration of external knowledge sources for language processing, specifically biomedical text processing. He has a master's in artificial intelligence from Ferdowsi University of Mashhad, Iran, and a bachelor's in computer engineering from the University of Birjan, Iran. And currently, he is a postdoctoral fellow at McGill University, where he focuses on natural language processing techniques to leverage clinical text reports for cancer outcome prediction. So I just want to start by thanking very much Dr. Bagazadeh for taking the time to be here today with us and to teach you some content on deep learning. And I just want to remind you that unless the speaker asks for a question time, you might still ask question, but put them on the chat. And then if the speaker says it's Q&A time, then feel free to unmute and ask your questions. So now I will leave the floor to you, Parsa.
Thank you,
And
Sebastian, for the introduction. Hello, everyone. I would like to thank first the AI Research School for inviting me again. I also was an instructor last year for the same topic. This year, I'm very glad to join again. So I'm going to share my screen now. So now you can see the screen, right?
yes, we can.
Okay. So hello again. Thank you for the introduction. As Sebastian mentioned, I'm Parsa. I'm a postdoc at McGill University. I have a PhD in computer science. I focus on natural language processing in my PhD. Right now, I'm doing research on medical informatics, precision oncology, natural language processing, and deep learning. So today we are going to talk about deep learning fundamentals. So we are going to start knowing what are the neural networks, the building blocks of these models, how is the training, what are the challenges, and so on and so forth. So let's first talk a little bit about the history of artificial neural networks, or ANNs. So ANNs are inspired by biological neural networks that we have in our body and in our brain. In fact, the first attempt of having an artificial neural network was done by Pitts and McLeod in 1943. They basically created a mathematical model of how neurons might work in our brain. So what was the purpose? The purpose was to basically create a computer that can act and think and have an intelligence like a human. Then in 1958, a very big leap was done in and was taken in ANNs. Rosenblunt proposed the perceptron algorithm, which is a very simple approach for linearly classifying the different data. Later, we had backpropagation algorithm, which was used for multi-layer neural networks. Before 1980s, the training of neural networks, it was mainly limited to single layer or very, very shallow neural networks, but the backpropagation algorithm allowed to train more deeper networks. But for several reasons. In the beginning of so in the 1990s, neural nets, they fell out of favors, and what we call it and what we refer to as AI winter. The reason was that mm, they become very difficult to train, uh, and there was no efficient approach or method to allow to train these deep neural networks. And in 2000, a renewed interest was found in deep models for several reasons. First, we had more data, we had more annotated data. Second, we had more capable machines that were allowed us to do computation faster. And in 2010 afterwards, we had a variety of new deep models like GANs, autoencoders, and transformers. And this transformers right now is the building block of many language models, uh, which ChatGPT is one of them. So let's talk about feed-forward neural networks. Feed-forward neural networks are the most basic form of neural nets. A single layer, actually, a single layer feed-forward net is basically a mapping that maps an input that I'm denoting it by x. This x is a vector, in a space with d dimensions. So it's a vectors with d of n entries. So we have maybe in 100 dimensions or 200 dimensions, we have a vector that you already know what this vector is. This is a feature vector that you saw in classical machine learning. And the objective is to learn a mapping that maps this input to an output vector. This output, we'll discuss what this output is and what the size of this output and what is actually what this output mean. Nevertheless, so this mapping is actually characterized by a weight matrix. This weight matrix that I'm showing it with the W, this is called a learning parameter of the network. So formally, I'm writing this, that y is a function of x times w. So when people say neural network, don't be afraid that this is something very strange. In fact, neural networks are simply a bunch of matrix multiplication and addition, as you will see throughout this lecture, and we will see in the next sessions. There are only a matrix multiplication. So we are multiplying the vector x by the matrix W, and we are actually mapping it. So this would characterize a mapping, and we would obtain a W. So what is this f? For now, let's assume that this f is an identity function. So what do I mean? I mean that on the result of this multiplication, we are not changing, we are not altering the result. So we are keeping the same result that we had from this multiplication. So how do we, just to remind you, how do we multiply matrices and vector and matrices? So suppose we have a vector like this. It's a one times 5 entries. So in this case, d of n, or the dimensionality of our input, is 5. It's multiplied by a matrix of 2 times d of out. The 5 times 2, which I'm considering d of out to be 2. Okay, and I would obtain an output y. So how do we perform this matrix multiplication? This row by this column. So this entry times this entry times the corresponding entry, and so on and so forth. And the result is aggregated in this entry of this vector y. If you see, we have a net-like connections here. we are obtaining this by multiplying and traveling this path and traversing this path. So, and that's where the terms neural net, the network comes from. So, or I can abstract it further and represent a single layer feed-forward network like this. So right now, the size of the output, it's not our concern where the size of output comes from. I would talk about this, how we should decide what is the size of output, uh, and so on. So for now, I want to introduce mm, mm, TensorFlow Playground. TensorFlow Playground is a web-based tool that you can play around with, and you can actually tweak it and train simple neural networks on different data sets. So the purpose of a single layer neural network is to find a linear discriminator and to separate two classes. Here, as we can see, the class with the blue dots. If you want, I can zoom in, the class with blue dots and the class with orange dots. So the purpose is to find a discriminator line that basically separate these. So here I can start a training process. We would talk about the training process, how it is done. But right now I found a separator line using a very simple neural net without any extra layers. Only the features are mapped through to an output by a single mapping. So now I have a discriminator. It's discriminating and it's basically classifying and separating the two different classes. Okay, so but it's not always the case that the classes and the distribution of data is linearly separable like this. We might have linear non-separable distribution, something, for instance, like this. You see that the two classes are not linearly separable. Okay, so it means that if I start the training process, we can see that it cannot and it fails to find a discriminator surface or discriminator line or whatever you wanted to call it between the two classes. So what should we do in this case? So in such cases, we usually go toward multi-layer feed-forward networks. Multi-layer feed-forward networks, they basically comprise of consecutive projections. So in a single layer neural network, a single projection, here we saw that this projection was characterized by this W. Now, so we had a single projection. Here, we want to have consecutive projections. It means that we would have more layers, as we call it, and we would have a multi-layer network. These intermediate layers, we are calling it often hidden layers. These are layers that fall between the input layer and our output layer. So each of these projections are again characterized by a weight matrix W. Here, the input by this projection is mapped to an output H1. Here we would have a hidden representation, H1. Then H1 is being mapped using W2 to H2. Here we would have H2. And finally, using the final projection, the W3, we are mapping H2 from here to the output. So here we had two intermediate hidden layers. So, and I actually made the network deeper, and I have increased the number of parameters. Here I had how many parameters? So 1, 2, 3, 4, 5. 5 was the dimensionality of the input, and the hidden dimensionality is 1, 2, 3, 4, 5, 6. So overall, I had 30. I have 30 parameters to learn, and in this weight matrix W1, it has 30 entries that I need to learn, and I have increased the number of parameters. By doing so, I'm hoping to give the network more discriminative power and allow it to predict or approximate more complex functions and more complex distributions. So if I go back to the TensorFlow playground, you can see that I can add more hidden layers here. So let's add three hidden layers. In each hidden layer, I would have three neurons, or the number or the dimensionality that I'm mapping the input from the previous layer to that dimensionality. Here I'm adding 5. Here I'm adding, for instance, 3. Here I would have maybe 3 neurons, 4, and here I would have 3 neurons. So let's see whether we actually allowed the model to better discriminate this complex distribution or not. So here I have increased the number of parameters. I have made my model deeper. I'm going toward deep models here, but as you can see, again the model is failing to draw any separator line or any separator surface between the two classes. So what is the reason here? What is the reason behind this? So the question here is that did we actually increase uh, the learning capacity? By learning capacity, I mean whether we can approximate more complicated functions, or we can separate more complex distributions or not. So let's see. We can actually rewrite the output y as this equation. Remember, I had this. So this y is is obtained using H2W3. H2 is obtained by H1W2, and so on. So I can consider this as consecutive projections, right? So x times W1, W2, and W3. And we can substitute this W1, W2, W3, because the multiplication of W1, W2, W3 is itself is a matrix. I can substitute it with W tiled. And I can, interestingly, I can again reduce this form to this form that we had in a single layer network before. We had this form in a single layer network before. So it means that this multi-layer network is reduced to a single layer network. And apparently, depending of the network, even though I have added many more hidden layers and I made the model deeper, it doesn't not necessarily lead to more learning capacity or a better classifier. So remember, at the beginning we had an assumption. We had an assumption that this function that I would introduce, what is this function is, I consider this as to be an identity function. Okay, so basically by doing so, I made this projection a linear projection, because it does not change what was the result of this linear projection. Okay, so how we can do it? So now it's time to consider different options for this f, and actually consider activation functions. Activation functions are actually used to add nonlinearity to a network. Here, when I had an identity function, I had a linear approximation, a linear neural net. But I can, instead of choosing an identity function, I can have different choices for my activation functions. I can have rectified linear unit, or ReLU, which is a piecewise activation function. It means that from -infinity to 0, it is 0. So it's a linear function from -infinity to 0. And from 0 to +infinity, it's also linear. So overall, this is a nonlinear function, but piecewise, it's a linear function. Or I can have sigmoid function. Perhaps this is one of the most used and commonly used activation functions in neural nets. The sigmoid function actually squashes or maps its input to the 0 and 1 interval. So it doesn't matter what input you're giving this to this function. If you give about 8, it's about 1. If you give 2, it's about maybe 0.7. And if you give 0, you have a turning point at 0.5. And for negative values, we have values below 0.5, and for positive values, you would have values above 0.5. Or we can have hyperbolic tangent. It maps its input to -1 and 1 interval. So apart from the mapping, all of these three mappings are actually nonlinear mappings. So these activation functions, they give this, and they give the network the ability to approximate more sophisticated functions. And actually and we are hoping by having and introducing these activation functions and using, instead of an identity function, to use an activation function to basically classify and separate more complex distributions and linear non-separable distributions. So how we are using these activation functions? These activation functions are applied to the output of each of these layers. So the output of each layer in a feed-forward network, as I mentioned before, is a vector. The input was a vector, the output and the intermediate representations, the are vectors, and the output, again, is a vector. So by having a vector, I'm applying a sigmoid here, a sigmoid activation to this vector, and I'm applying the sigmoid activation element-wise. How? I'm taking -1.0044, and I'm giving it to the sigmoid activation function. It's somewhere here, and then I would obtain 0.26. Or 0.88, it's somewhere here, I would obtain 0.70. Or 1, I would obtain 0.73. Okay? So now let's go back to the TensorFlow playground. Here, we can see that from the very beginning, I made this choice to have an activation function, linear activation function. So which basically corresponds to an identity function. Here I can change it to those options that I had, to sigmoid, a rectified linear unit, or hyperbolic tangent. I would use ReLU, for instance. And if I restart the training process, we can see now all of a sudden, even though I have not changed the structure of the network, we can see now that this network has been able to separate the samples from the two classes without any complications, and it did a very easy job doing so. So the question here that we should ask, I told you that we don't right now, we are not worried about the shape of the output. So we know that what is the shape, where the shape of the input comes from. So in your machine learning, in your classical machine learning sessions that you had, your samples, whether it might be a patient, it might be a flower, it might be an animal, it might be some test results, it doesn't matter. Your samples, they need to be represented by a set of features. So how many features, for instance, we might have for a certain sample? Here I might have 5 features. So that sample is represented by 5 features which would determine the size of the input to my network. But how about the size of output? The size of output for a classification task. The size of output actually corresponds to how many classes do I have in my data set, or I'm trying to classify a sample to how many categories. For instance, if you want to categorize based on a digit, here in a case of digit classification, we would have 10 different classes, starting from 0 and 9 classes for the rest of the digits. So if we have a binary classification, we can assume and consider only a single output, okay? And if we have two classes, we can consider one output and apply a sigmoid activation at the end. So what was the behavior of a sigmoid activation? The sigmoid activation actually it again maps the input, map its input above zero point 0.5 or below 0.5. And this 0.5 can be a decision threshold that if the network is producing a prediction or an output below a negative prediction, it would be below zero point 0.5. And for instance, we are assigning it a negative label. And if it's above 0 and it's positive, it would make the output and map the output to greater than 0.5, and we would decide that that example and that sample belongs to the other class. But if we have more than two outputs and or two classes, and we actually have a multi-label classification task, or we have C classes, we are considering C outputs or C the size of output. We are going to map it by tree here, or C in general, and we are going to assign each of these neurons or each of these outputs to a certain class. Okay. And then we would apply a softmax activation function to, again, this vector, because as I mentioned before, the output or the hidden representations or the inputs, all of these representations are vector in a feed-forward neural net. So I would apply a softmax activation. This softmax activation, again, is applied element-wise by taking the exponent of each element and dividing it and normalizing it by the sum of exponent of all of the dimensions. So the result here would be that each of these elements in the output, after applying softmax activation, they would have a value less than 1. And the summation of all of these values would be equal to 1. So when we are talking about this, so we know that in probability, the summation in probability theory, the summation of all of the expected outputs and the probability of the expected outputs and the expected events are summing up to 1. So here, actually, by having a softmax activation, we are having a probability distribution at the output. And the neuron with the largest probability would win the classification decision. And for instance, if this neuron uh, has a largest probability, we would assign this sample, the input sample, as class 2. So that's where the output shape comes from. How many classes do we have? If you have two classes, we would have a binary classification. The only one output is enough. We then apply sigmoid activation and then do a threshold based on 0.5. If you have more classes, we can apply the same number of output and have the same number of outputs. So now let's talk about how we are actually going to train a neural network. And because these parameters that are doing the mapping, these parameters are randomly initialized, okay? And through some sort of learning process, these parameters are adjusted such that the label that we are expecting and predicting at the output would be the same label that was provided by the experts, by those who annotated the database, the data set, and actually have zero error. So to do this, we are using loss functions. Loss functions, they measure the closeness of the prediction and the target. Here, I'm showing my prediction by y hat, and the gold label or the target that was provided to me as y. So, and this loss function, which measures the closeness of how much these two are close to each other, is used during the training process mm, and is used to guide the training process to update its parameter, the parameter of the network. Some of the frequent and commonly used loss functions are MSE, mean squared error, cross entropy, hinge, hover, and depending on the type of problem at hand and that we want to address, whether it's a classification problem or a regression problem, we would use different loss functions. For instance, MSE loss is a loss that is often used for regression problems, or cross entropy is used for classification problems, specifically for multi-class classification problems. So cross entropy is defined like this, assuming that we would have a vector of gold label like this. What do I mean? So here, apparently, I had by the shape of this output, I had, and by the shape of the prediction that was provided to me, I had a 4-class classification problem. So remember how many neurons I had at the end of my network, the size of and the number of neurons, the size of the output determined the number of classes. So here I had 4 classes and 4 scores, probability scores, the output of the softmax, as the confidence and the probability that I have for each of these classes. So here, for the class 1, I'm 30% sure. For the class 2, I'm 40% sure. For the class 3, 10%, and for the first class, 20%. Okay. However, as you can see, the gold label and the target actually corresponds and shows that the sample belongs to class 1. Okay, so it means that, and here the largest probability belongs to class 2. It means that my network has committed some error. It also produced a relatively large value for class 1, but at the end it chose class 2. So it means that I would have some error. I would calculate the error. So the loss, cross entropy loss, is defined like this. For each of the dimensions that I had in my target vector and in the prediction, I'm multiplying these dimensions. So one times the log of 0.3. So I have 1 times the log of 0.3, and then 0 times the log of 0.4, 0 times the log of 0.1, and so on. So these terms are 0, and overall, since the log of 0.5 is negative, I would multiply a negative 1 here to have a positive value for the loss, because I want to show that there is a magnitude to this quantity. So the loss for this case would be 1.73. So a question is that how about if the network is 100% sure about the prediction? And for instance, the target is 1, and also the prediction is 1 here, and the rest is 0. So in that case, I would have 1 times the log of 1. The log of 1 is 0, and overall, I would have a 0 loss. So it means that when the network this loss function is designed, and most of these loss functions are designed such that if the network has a 0 error, the value of the loss would be 0. And this loss needs to be minimized. And how I can minimize this loss? By adjusting the parameters of the network. Why? Because this loss, if you see here, it's a function of the prediction here, right? So well, during the training process, the target is a constant. So we are not changing the target. So this loss value is actually a function of the predictions, and the predictions themselves, they were function of the learning parameters of the network. So if we want to reduce or minimize the value of the loss, we need to adjust the parameters of the network, or those W's that I had in the network. So how we can adjust and minimize something. If you remember, if you wanted to minimize and find the minimum of a function in Calculus 101, you had that function, you took the derivatives of that function, and you said you can set the derivative of that function to 0. And then you can find at which points in the domain the value of the derivative is 0. For those cases, we would have minimum values. So we already saw this in Calculus 101. But the point is, it's not always the case that we would have easy functions that we can easily take the derivatives. And ANNs, they often, and artificial neural nets, they describe non-convex functions. Why non-convex functions? Because I introduced nonlinearity to this network. It's not a linear function anymore, or it's not it's not a quadratic function, a simple quadratic function like this anymore. It's more a more sophisticated function. So it means that when we have a non-convex function, I would have several local minima. So there is a one minimum here, one minimum is observed here, and one minimum here. So the question is how to choose which of these minima. So to do this, actually, we are using gradient descent approach. Gradient descent, it's an iterative approach that at each point uses the derivative or uses the gradient of the loss. The gradient of the loss, for instance, if you're at this point, the gradient of the loss shows the slope of the function, just like the derivative did, and shows the descending direction of a function. So if we take the same descending, if it move on this surface, which shows the error surface or the lost surface of this neural net, if we go toward that direction, we are actually making our we are actually obtaining a smaller loss or a smaller error. So based on the value of the gradient for current sample, we can update our parameters. That here I'm showing it by theta1 and theta2. So these are basically, they can be considered as the entries of those matrices, W matrices that I had. So how we do it? So here we are at a point that I have a specific theta1 and theta2. Here I'm denoting it by theta old. I'm at this point. Then I'm taking the gradient of the loss toward moving toward a certain direction with a step size that we call it. So this eta step size, we are calling it learning rate. So by a certain pace, we are actually moving in on this error surface or the loss surface, and then we would obtain a new value for our parameters. Since we have a new value for our parameters, now this time the error would be different compared to the previous training step. So, and how we are actually applying this gradient. So we have some approaches and a schema for how to update these parameters. So optimizers, they are responsible for updating the parameters that we have in our network. So we have different optimizers: stochastic gradient descent, RMS-prop, ADAM optimizer, or adaptive momentum optimizer. And each of these optimizers, they have a different scheme for updating the parameters. And Note that all of these optimizer, they operate based on gradient descent, and they assume this procedure moving in moving around the Earth's surface. However, the step size and the way that this gradient and this update is applied is different for different optimizers. For instance, what is the consequence of having different strategies for updating these parameters? So sometimes the optimizers like such as a stochastic gradient descent, they usually get stuck in sorry in some flat places like plateaus, and they fail to actually go toward the a better minimum. But for instance, optimizers like ADA Delta or ADA Grad, they have a better updated strategy, and they can escape these flat regions again that we are calling these regions plateau. So depending on the updated strategy that each of these optimizer they have, uh, they might converge to the solution, or converge to the area with the least error, or they might get trapped in such areas. And then let's put things together. Now we know what to do. So we have a set of training samples. This is a supervised learning model. We have a set of training samples. Each training sample is represented by a vector X and by a gold label of Y. So we have a set of ordered pair in our training set. So we loop through these training set. We provide each of these samples to our model. That here that neural net. I'm abstracting it with F. It can be a single layer network or a very deep multi-layer network. So the result of this function would be a prediction y hat. Then I would calculate the value of loss. If we have a multi-layer label classification problem, I would have cross entropy, for instance. Then we take the gradient of the loss. We have a gradient. We have the gradient of the loss, and we ask an optimizer to apply the gradient of the loss. So this optimizer, again, is responsible for updating the network parameters with following the gradient descent strategy by taking the gradient of the loss and subtracting it from the current set of learning parameters, moving toward the direction, the descending direction, and obtaining a set of new parameters. So these optimizers, these different optimizers are already provided by different deep learning libraries. So you don't need to worry about how you want to apply and update your learning parameters. So just before going to into the implementation, I would like to introduce autoencoders, because until now I talked about a supervised learning setting where we had both X and Y, so the input and the target. But we also have unsupervised learning. In an unsupervised learning, there are no target labels associated to samples. And the idea is to actually learn rich representations from the features. So, for instance, one of the unsupervised learning models is autoencoder. Autoencoder has, so basically it's again a feed-forward neural network, an autoencoder. You can see that the input is mapped through several consecutive mappings, is mapped to an output. But the point is, in an autoencoder, the input is reconstructed at the output. We have the same number of neurons here, and the objective is to actually learn a representation that can basically map the input to an output. So one might ask, what is the benefit of just copying the input to an output? So the benefit actually lies in this intermediate part that we call it an autoencoder bottleneck. So an autoencoder is comprised of two parts: an encoder and a decoder. The encoder first compresses the output into this intermediate representation, and then this decoder is used to reconstruct and use the representations provided by this intermediate part at the output. So so the benefit is that once the training of this network is done, you are getting rid of this decoder part, and you would use this encoder part as some sort of a dimensionality reduction model. In many applications, the input dimensions are very we have a large number of inputs, and we want to reduce the number of features. So we can use an autoencoder and then obtain representations in a smaller space. So now let's implement, and let's talk about the implementations. Anybody, do you have any questions so far?
I think there are a lot of questions on the chat, Parsa, if you want to address them.
Okay, so let me see. So many questions. So let's start from the beginning. So the dimensions are columns here. So yes, so Elham Ali has asked the dimensions are columns here. So actually, it depends on the designer of the system. And it depends on how you want to structure your data in your tables. Some assume the dimensions and the features to be columns, but there are also other conventions for storing tabular data and storing features. For instance, other conventions use the rows as the features, and assume the column to be columns as the input sample. Linear layers and activation functions were covered. By whom, Sebastian?
No, they were just asking people because some people connected late, so I was just saying what was covered.
Okay, so it's asked. I didn't get what softmax is and how it is used. Okay, sure. So let me go to softmax. So softmax, just like these activation functions, ReLU, sigmoid, and hyperbolic tangent, is an activation function. Okay, softmax, again, softmax is applied to a vector here, to a vector of you see these this is a vector of d dimensions of d elements. Again, just like ReLU, sigmoid, or hyperbolic tangent, it is applied element-wise. So I'm taking the exponent of each of these elements here, h1, and then divide it by the summation of the exponent of all of the elements that I had before. Okay. So what would be the effect here? That each of these elements in the new vector that I have, what would it be? It would be below 1. And the summation of all of these elements would be 1. And actually, it produces a probability distribution and it obtains a probability distribution from the output. And then the output with the largest probability and the largest value would correspond to the prediction class that we make. So why the cross entropy is often used for classification. So cross entropy is one of the losses that are used for classification. So for instance, by default, if I want to if somebody asks me to write a piece of code for multi-class classification, I would use cross entropy. Why? Because it also it also covers the binary classification setting, because a multi-class classification is also binary classification. You can consider two output at the output, two neurons at the output of your model, but it's easier to train for certain learning algorithms. But as I mentioned before, there are different loss functions like hinge loss. Hinge also is used for classification and so on. So what do you mean when it says 30% sure? That's a good again, that's a good question. So 30% sure, as I mentioned here, we have probabilities. So when we are having probabilities, we are talking about certainties, and how much we are sure that, or how much we are confident that a model would or an event might happen. Okay, so here the event of having a prediction of class 1 is 0.3 or 30%, because you can always express a probability in percent. So that what I mean, what I meant by being 30% sure. So everyone, I just joined, could ask any question. So let's see. So the theta in our gradient descent is a vector quantity or a scalar quantity? That's a very good question. So Aaron asked this question, so I'm repeating the question. The theta in your gradient descent algorithm is a vector quantity or a scalar quantity. So in fact, this notation that I provided from gradient descent, it's theta here is actually I can consider it to be both scalar, a vector, or a matrix. Okay. Overall, it can be a matrix. Here, when I'm talking about gradient, we are defining the gradient for vectors and for vector spaces and for matrices. But overall, if for instance, if you consider this to be a scalar, this gradient would be reduced to the derivative of that function at that point. So here the theta 1 here, theta 2, it's in this case here, it's a scalar. It's it can be considered as one of these entries in the weight matrix. So each of these entries in this weight matrix is a learning parameter, or here the convention here is to show the training parameters by theta. So yeah, but the gradient descent. So Rishba, they ask about the fact that gradient descent will only give us the local minima, assuming random starting point. Yes, absolutely. So if you start from here, the result of your gradient descent updates would be here, and then you would terminate your training process here. But you start from here, you would end up at a different point. That's why if you train a neural net several times, you might have a slightly different performance at the end. So yes, absolutely, Aaron, you're right. As I mentioned, you're saying that you're using it like a scalar quantity, but the gradient is a vector. Absolutely. So here I'm assuming that these are vectors or matrices. So let's so now I think I answered a fair amount of questions. Let me go to the actual implementation. So can you see my screen? Sebastian, there's this
yes, we can see the notebook.
So let me share this notebook with everyone. Let me copy the link, and then I would share it in the chat, so anyone can have access and run simultaneously if they want. So now we are at the point that we are going to implement our first neural network. So for doing so, I'm going to use the PyTorch library. PyTorch here is a Python library developed by Facebook. It includes many readily available classes and methods for implementing neural networks. So you can import PyTorch in Python. You can import it using Torch, and it has, so as I mentioned, it has many classes and methods. And one of these sets of methods and classes are neural layers, and then you can import those neural layers like this. Import torch.nn as nn. So I'm going to reference this nn in my code. So let's import it, and then we are going to uh, to have our first simple single layer feed-forward network. So here I'm actually implementing the code. I'm doing an object-oriented approach, and for this I'm defining a single layer network class. And this class is a torch. I'm defining it to be a torch module. So I'm going to say why, I'm going to justify why I'm doing this. But for now, so here I am defining a simple class. In the initialization part of this class, I'm only considering an input layer or a single layer. How? I'm saying NN. Remember, I already imported these set of standard neural layers, and NN linear. So I'm importing I'm defining a linear layer. So, and this linear layer actually corresponds to a simple projection, or one of those W's that we had in our case, right? So, but this right now, this is an arbitrary projection that I'm putting here. It's again a W. The input size of this or the number of rows in this matrix is 64, and the number of columns is 10. Okay, so I have a 64 by 10 matrix as my projection, as my only projection, since I have a single layer neural net here. Okay. This is the only thing that I need for a single layer neural net. And then I would define a function called forward, a forward function. This forward function takes the input that is provided to this neural net. It's again a vector, and then uses this method, the input layer, this projection as the input, and it obtains and it yields an output. And I'm returning the output. So it's a very easy class. So what is the benefit of having a class and defining neural network as a class? Then I can define multiple objects of this class and multiple instances of this class, and train different and have different models for myself. So here I'm defining a single layer net. I'm making an object called model out of this single layer net. Then I have a random. I'm just having a random input, just a random vector here. I have a random vector. Okay, of the size 64. Remember, this linear projection had what? Had 64 rows and 10 columns. So these sizes are totally arbitrary at this point. So if I go back, just go back to my first slide. Here, you see, at my input, the size of input was d of n. So in this case, I define a random input of 64. So I have 64 elements in my input. Okay. So what is the size? What should be the size of this W projection W? It should be again d of in, or 64, and d of out. So which in this case I have considered to be 10. So here this simple neural net actually maps an input of size 64 to an output of size 10. Okay. So now I'm providing this input to my model as an input argument. But here, see, if I note that I have defined here, I mentioned I defined this singular net as a torch module. Okay. So by default, if I define this singular network as a torch module and I devise and I implement a forward function, by default this forward function would be executed. Okay. So now let's run this model. Okay. So here, the input was provided to the network. It went to this forward function. It called this forward function. The forward function passed this input to my input layer, the projection that I had, and then returns the output. So if I look at the output, the output looks something like this. You can see it's a simple set of elements. How many elements? It should be 10 elements. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Just to again iterate and repeat, if we consider if we define the class as a torch module and we implement a forward function, by default, if we call the model like this, it would call the forward function. So now if I change the forward function and change the name of forward function to another name and try to do the same thing, here you can see that it raised an error. You see that the module single layer net is missing the required forward function. Okay. So now here I change it back. It would run perfectly. Here, in addition to actually looking at the content and the content of the output, what it looks like, I can also look at the shape of this output by invoking and using this shape attributes that I have. Okay. So the shape of the attribute, the size of this output is 10, just like I asked it to be, because I projected this input of 64 to an output of size 10. Okay. Now let's add more layers. So here just by adding more, having more in the initialization part, now I'm having a multi-layer network. Again, I'm considering it to be a torch module. Here, by having more projections, remember how we had a multi-layer feed-forward network? I had more projections. So each of these projections correspond to they correspond to a linear layer here. So I would have an input layer, then a hidden layer, then an output layer. If you see, and these dimensions are totally arbitrary. The input layer is supposed to take an input of size 64 and map it to 128. The next layer maps 128 to 32 dimensions, and finally 32 dimensions to 10 outputs. Okay. So I declared and I defined more layers, more instances of this linear layer. And then in the forward path and in the forward function, I define how these layers should be invoked and should be executed. So the input is provided to the out input layer. Then I have a hidden one. Remember, I had a hidden one here. Hidden one was the result of the projection of the input by the first linear projection. Okay, the input layer. I have H1. Then H1 is provided to a hidden layer H2, and the H2 is provided to an output layer, which maps the H2 to an output. Okay. And in the meanwhile, I also put two printf statements here to actually look at the intermediate size of these hidden representations. Again, so now instead of having a singular net, I'm going to have a multi-layer net, an instance of a multi-layer net. Again, I have a totally random input. This input has a size of 64, and then I'm providing this input to an output, and I'm providing this input to the model. Again, the forward function or forward method would be executed and called, because again, this is a torch. I have defined this as a torch module. Now let's run this. So here, as intended, the size of H1 is 128. Why? Because H1 was the result of the input layer. Input layer mapped its input to 128. And the size of H2 is 32, just like intended, because the H2 comes from the hidden layer, and the hidden layer maps its input to 32 dimensions. Okay? So still, even though, again, I have multiple layers here, the point is still it expresses a linear function, because I have no nonlinearity. And then I can add nonlinearity. As I mentioned before, the nonlinearities, I'm going to apply it to the output of each of these layers. Okay? So now instead of just passing the output of each layer to the next layer, I would apply first a nonlinearity. Here I'm using ReLU nonlinearity. In the next layer, I can use a hyperbolic tangent nonlinearity. Okay. So the only thing that I changed compared to the previous implementation of this multi-layer net is that before passing the H1, the input of each, the output of each layer to the next layer, I'm going to apply nonlinearity and nonlinearity here. Now, if we look at the output, so you would have an output like this. Okay. Note that the last output here, I have not applied any nonlinearity here. I can apply nonlinearity, for instance, ReLU, I can apply it. See, note that I have negative values here, right? For at this dimension, I have a negative value. This dimension, I have a negative value. So if I choose to apply nonlinearity here, I can say torch.relu as a nonlinearity. And I'm expecting that this nonlinearity, because of the characteristic of the ReLU activation, I won't have any, I shouldn't have any negative values at my output. And you can see all of the negative values here are turned to 0, and the positive values are kept. Here, if I go back to my activation function, the ReLU activation, all of the negative values are mapped to 0, and the positive values are kept as they are. So now I have a here I have a multi-layer network that also has nonlinearity, and I'm hoping that this network would be able to approximate complex distributions and basically to categorize complex distributions of data with nonlinear distributions. So to actually use it, I'm going to try use the MNIST dataset. So what is the MNIST dataset? You can look online. The MNIST dataset is a dataset of classifying digits. So digits from 0 to 9. These digits are in grayscale. So and the objective is to learn a classifier that is able to successfully classify digits. So I'm going to this MNIST data set, or the digit data set, is provided in scikit-learn, and I'm using scikit-learn data sets to import it. And then I would import it using this load digits. Then if you remember from your classical machine learning tutorials, the development of a machine learning model involves training on a train set, and then evaluating a model on a holdout test set. Okay, so I'm going to use this train test split function that is again provided to me by the scikit-learn machine learning library. So and I'm going to pick 20% of the original data for the test as test, and the rest for the training. Okay. So now let's look at this data set before discussing more. So each of these images in this data set is has is is defined by 8 pixels as rows and 8 pixels as columns. So it's a 8 by 8 pixel image. Okay, so overall, how many entries do I have in this image? 8 by 8 image. I have 64 entries. So uh, as I mentioned before, the input to a feed-forward network should be a vector. Okay, and now here we have been provided with a matrix. Okay, so somehow we have to convert this matrix to a vector. Okay, so how we can do it? We can actually flatten, as we call it, flatten this image and concatenate all of these rows in a single row. So we would keep this first row. We would move this second row to the end of this row, and all of these we are going to concatenate all of these rows within the same row, and we would have a 64 long vector as the input of our model that basically represents an image. So here we can see an image of digit 0, and the next image, these are two different images that I picked randomly. It shows a 5. Okay, so uh, now let's go to the training of this model. So in addition to having a model, we also need a loss to capture the closest and measure the closest of our predictions and the targets, and an optimizer. So I'm using a cross entropy loss, which is also provided by PyTorch library as a loss function. I'm making an instance of this loss function, and I'm also importing Atom optimizer from torch.optim that stands for optimizers. I'm making an instance of this optimizer. Remember, I mentioned that the optimizers are responsible for updating the parameters of a model. So I'm giving the parameters, the set of all of the parameters of this model to this Atom optimizer, and I'm setting the learning rate or that step size that we had before to 0.001. So here, this eta, which I mentioned, it is called learning rate. I'm assuming this as my learning rate. So the choice of the learning rate would affect the quality of the training process, but we would discuss it later. As I mentioned before, I'm now ready to loop over the training data. Okay, I'm ready to loop over the training data. So I'm looping over this training data. First, I'm making sure that there are no gradient stored in this model from the previous passes. I'm providing here again. I'm providing the training data to my model. Okay, this instance of the training data to the model. I'm getting the prediction. I'm providing the prediction and the gold label, the label that corresponds to the current training sample, to the loss function, and this loss function would calculate the value of the loss for me. And to calculate the gradient of the loss, I would invoke loss.backward. It's a built-in method uh, in the neural layers that is implemented in PyTorch. This loss.backward calculates the gradient of the loss, and then the optimizer updates the parameters of this network. Okay, and to evaluate the training process and see where the training is going and how much what is the value of our loss. I'm storing the value of the loss in each path. So usually in training a neural net, we would go through the training data for several, what we call it, epochs, or several passes. So one time might not be enough. So we are going to give the samples to the model several times. You are going to expose the samples to the training model several times and for several epochs, and then until we would have a small value for our loss. So here, for each of the passes that I went through my training data, you can see the value of the loss, whether the value of the loss is getting degraded or not. Okay. In this case, the value of the loss is not going down. The reason is that here at the end of this layer, I consider this as a ReLU activation. Okay. Here I'm going to compile it again. I'm not going to put a ReLU activation at the end of my network. Then I'm going to compile this training process again and hoping that the loss value would go down. Here, as you can see, the loss value is going down, starting around 1.9 to 1.2, 1.8, and you can see it's going further down until 10 epochs. So now let's talk about the effect of our learning rate. So let's assume a larger learning rate for this network. Okay. And let me compile the model again because I want to initialize the model from the scratch with new random parameters. And then let's run this training again. So you see here the value that I had here, the value that I have for the loss, it's not changing. So why? Even though I chose a larger learning rate for my model, why it's not changing? The reason can be traced back to this figure. If we are choosing a large learning rate and a large step size, we might oscillate through this error surface. And from here, we might jump to another side of the error surface, and again jump to another side, and oscillate on the error surface. So this shows that the learning rate and this step size should be chosen carefully and with respect to the value that we are seeing for the loss. If the value of the loss is oscillating, it's not changing, the learning rate might be very, very large or very small. Now I'm considering as a relatively smaller learning rate. Then let's compile and let's have initialize our model again. Now that I have a smaller learning error rate, let's loop through the training data and see the effect of choosing this learning rate. Now you can see the network is converging toward its its minimum loss faster compared to the original learning rate that I had. So once the loss is at a satisfactory level, we would continue to make predictions for our test data. That making predictions for the test data is just like making predictions for the training phase. But the point is, in the test phase, you are not actually you are not making any update for the parameters, and we are not calculating any gradients. So here I'm declaring that I won't need any gradients when I'm providing these test samples to my model. Okay, so a test sample is provided to a model. A prediction is provided. If you remember, I mentioned that for multi-class classification problem, I would have a prediction, and the largest index or the largest dimension that has the largest value would correspond to the class that the model is predicting. So to obtain this largest index, okay, I'm taking an argmax, the maximum argument, this argmax function method. It returns the index of the element with the largest value, the output to the largest value, and then I would have the predictions. I would have all of the predictions, and I would use the classification report from scikit-learn library to have a report of the performance of my model. So now you can see that for different classes, remember I had 10 different classes corresponding to 10 different digits from 0 to 9. For each of these classes, this classification report provides an F1 score, um, precision and recall. Overall, you can see that for most of these classes, we have a good accuracy, a good performance. For 8 and 9, we have a relatively lower performance, 94. Why? Because, for instance, it might be due to reason that 8 and 9, they might look similar sometimes, or 6 or 9, there might be similar sometimes. So that's pretty much about the implementation. I've also, as a bonus, I have also provided an implementation of the autoencoder. As I mentioned before, autoencoder has two parts. It has an encoder, it has a decoder. The forward pass of this autoencoder is to first encode encode the input, and the encoder to decode the input, decode the encoded input, and then to construct the output as at the input, the input at the output. So that's pretty much of my presentation. I hope that you had the chance to take a look at this notebook that I shared with you. If there are any questions, you can now unmute yourself and ask the questions.
Thank you so much, Basa. I think you already have some questions on the chat if you want to go through them.
Okay. So let's see. Yes. Is there a particular reason using an object-oriented approach? Yes, I mentioned that the benefit here is that once we define a model, we can make multiple objects of this model, and then provide this objects to for instance, machine learning beginners to train their model. So actually, we are actually designing some sort of a machine learning library and machine learning tool for beginners here, right? For instance, in scikit-learn, you also have classes for machine learning models or neural nets that you can make objects out of and then make predictions. Okay, so that's basically the reason to make it more usable for other people that they don't want to deal with the implementation details. They want to only make a model. They want to make an instance of the model and then get done with the training. They don't want to go through these steps. Does PyTorch allow you to be more functional? Absolutely, yes. We can also be functional and basically avoid some of these object-oriented approaches. But the point is, many of the PyTorch functionalities that are used, for instance, the optimizers, they usually assume that you have classes. So it would be more convenient for you to use the classes. So if you are overriding the original forward here, yes, absolutely, you can override the original forward. Okay, so let's go to the very first example here. As I mentioned, I had a torch module here. I mentioned that if we define it as a torch module, by default, if we assign a forward if we define a forward function here, the model would execute and call this forward function. However, this you don't need to use the forward function, the forward name. You can, for instance, use the fit, for instance, fit model. Okay, fit model. Okay, and in this case, since you don't have a forward forward function here, instead you should call fit model here. You should call this fit model, and then it would run perfectly. Okay. So, but here, if again I don't invoke and call the fit model, okay, and use the ordinary approach and ordinary way of calling the model, it would again would raise the error that the forward function is missing. So that's, yes, you're right. I did an override of the function. Wouldn't a procedural approach be better? Not necessarily. I mentioned that the benefit of the object-oriented programming is well established and well known to everyone. So why change up the activation? Why change up the activation function between layers? Aaron asked this question. That's a very good question that you made. Here, when I added nonlinearity here, I had the ReLU activation, and then I had a hyperbolic tangent application. Here, I changed the activation because I was able to do it. I could. I had this ability to it. I just wanted to show you that you don't necessarily need to use the same activation in different layers. You can here use a ReLU activation, and everything would be so it would work. It won't fall apart. So I used different activations because I could. So and that was for training purposes. So are there actual benefits? One can argue that there would be benefits to use different activation functions, but that is more related to the theory to the theory of training the neural net, and it's a little bit away from the scope of this talk. But it really depends on the application. It really depends on the complexity of your tasks. Sometimes it might be beneficial to use different activation functions. So this may seem like a dumb question. No question is dumb, but how we pass a value to a variable like this. So to self-input layer by the value of the input. So you see here in my multi-layer network or the single layer network that I had here. Okay. Here I define a layer here. I defined in the initialization part of this class. I defined a layer. Okay. This layer is actually so I'm saying a layer, right? It's actually a built-in method in PyTorch. The linear, it's a function actually. So if you have a familiarity and if you have worked with C++, for instance, in C++ you had the notion of constructors in C++, right? So where you initialize your parameters and the variables that you use in your program. So here I made an object of this layer or this method, and then I invoke the same object or the same method and provided the input to this layer. So the only thing that this does is to basically passes this input to the built-in linear, this built-in method, the linear method that was provided by PyTorch. So, however, the point is, you can. So what does this linear layer does is basically the only thing that it does is to it multiplies the input by a linear parameter by a weight matrix that is embedded within this linear layer. If I want to elaborate more, let's make a layer. Let's make an instance of this layer nn.linear. So I'm making an instance of that. So let's assume that I have 100 and I want to map it to 2. Okay. And let's print this layer. I want you to see what this layer looks like and inside this layer. So layer dot parameters. Let's see. So you see that the number of input features is 100 and the number of output features is 2. Okay, so actually it's a weight matrix. So linear. Let me see. Can I have more insight? Can I provide more insight into this? If you want to see what does it look like, you can go to PyTorch linear and actually look at the description of this layer in PyTorch website. You see, applies a linear transformation to incoming data. You see, it applies a linear transformation here. The linear transformation. So this is the same as the W matrix that I had before. So if you want to know more about how these layers are used with what functionality, you can always go to PyTorch and look for different layers. How do you determine how many input and output should be in the hidden layer? That's a very good question. That's a very good question. How many? What the hidden size? So we are referring to these intermediate sizes as hidden sizes. So these sizes or the size of hidden representations are usually determined based on trial and error. So for instance, you consider a small size for this. So having small hidden representations or having a small hidden sizes means that you would have less training parameters, or in other words the learning capacity of the model is you have a smaller learning capacity, okay, or a weaker learning capacity. So when you have a weaker learning capacity, your classification performance and the performance of your model might not be very good because it's not able to correctly distinguish between the two classes. So in that case, you can increase the number of hidden sizes and the number of layers, and then have more learning capacity and increase your basically performance. So how do you know what you should increase the size of your hidden layers or the number of hidden layers? Usually when you are doing the training, your loss, the value of your loss would not be decreased. The value won't decrease. So in that case, you can increase the number of increase the learning capacity basically. So I guess that was all of the questions. Any other questions? So I see that some of you like my reason that because we can, we do. Yeah.
If there is any other question, feel free to unmute and ask it. If there is no more question, this is perfect timing. Congrats, Pasa. That was
Oh, so
awesome.
I have to say it was maybe 15 minutes less so earlier than last year. I finished
Yeah. That's perfect, Pasa. That's perfect. And I feel like it was a great introduction to deep learning. You have been like very much into details about what's going on. So thank you so much for the time you took to prepare this.
Sure.
I
hope I could have been of any benefit to the understanding of you. You can it feel free to play around with play around with the TensorFlow playground, see how the choice of the number of hidden layers and the learning rate affects the performance of the model, and also feel free to change the and make a copy of the notebook. That's for you to work with.
Thank you so much, Dr. Pagazadeh. And
Sure.
for all our And actually, I'm sure the participants loved it because you have a lot of thank yous on the chat. So for the participants, I just want to remind you that now we're here with the deep learning fundamentals. We're going to have the tutorial on Tuesday, and then we're going to move to visual data, understanding exactly what's an image, and we're going to apply what Dr. Bagazadeh taught you today for image classification, for object detection, and then we'll move on to other application than images. So thank you so much, Dr. Bagazadeh, for your time, and thank you all for connecting on this Sunday night. We will see the ones who want to participate in the tutorial on Tuesday, and the next workshop, technical workshop, will be on Wednesday. Thank you all very much, and have a great night.